Humans are optimized to walk very efficiently. However, normal walking can be disrupted when humans carry heavy loads, which can injure or fatigue muscles and tendons. At the same time, for people with disabilities, they often have reduced function of their muscles. At Harvard, we're studying the biomechanics and physiology of human walking, trying to understand what makes that such an efficient process. We then apply this knowledge to the design of soft wearable robots that act in parallel with the body's muscles and tendons and mimic their function. With these systems, our goal is to apply small amounts of assistance to positively impact the mobility of both healthy people and people with physical disabilities.
When people think about traditional robotic systems, they don't think about something that can be worn by a person. When developing these soft exosuits, we start from the analysis of human biomechanics.
Human walking is so efficient in part because it's a passive dynamic process where the body and legs have a pendulum-like motion. The purpose then of muscles is to inject impulses or bursts of energy at the right time in order to maintain this motion. A key feature of our soft exosuit is a wearable garment.
We've created a garment that's close-fitting, comfortable, which is really important, and is designed so that the structure of the textile, the load paths that the suit creates over the body, mimic the function of the underlying muscles and tendons. And so when we apply force in the suit, this is acting in parallel with biological muscles and tendons.
With our actuation scheme, batteries and motors are mounted at the waist, and then we use cables to transmit forces to the joints. For a wearable robot to really help with walking, it's really critical to provide the right level of assistance at the right time for the wearer. For these systems, we need new types of sensors that are soft and can easily integrate into these wearable garments to be able to monitor forces and monitor movements. Using these two pieces of information, we're able to trigger when the actuation applies assistance.
The progress we've made in these human-machine interaction methods have allowed us to actually go out and walk in uneven terrain, avoiding obstacles. We can detect the different actions that the human is doing with the system being fully in sync to the wearer so that it feels very natural.
In addition to developing these portable, soft wearable robots, we're also developing a lot of lab-based equipment that allows us to very quickly understand the biomechanics and physiological implications from people interacting with these types of machines. This is important because still a lot remains to be understood about how best to apply assistance to people when they walk. A nice feature of our experimental approach is that we can rapidly explore different design architectures for the suit or different control strategies for our actuation system. We really call this human-in-the-loop testing, where as we develop these new components and features, we're rapidly testing them to try and understand if we're moving in the right direction. We're really excited about the potential for the elderly, for the military, for first responders, for people performing athletic activities. The potential is really just enormous.